Human preference isn't a single number. It's a structured, multidimensional judgment that spans semantic fidelity, spatial consistency, lighting realism, compositional aesthetics, and instruction adherence. Yet, when we align multimodal generative models with human preference using reinforcement learning, we routinely collapse that rich structure into a scalar score or a binary pairwise label. We lose the very dimensions that make evaluation interpretable, stable, and robust. And in doing so, we expose our training loops to reward hacking, distributional shift, and systematic biases like positional preference. This paper tackles that exact bottleneck. The authors argue that the problem isn't a deficit of preference knowledge in modern vision language models. The bottleneck is the absence of a stable, factorized interface for applying that knowledge. Their solution is a framework called Auto-Rubric as reward, paired with a training algorithm called Rubric Policy Optimization. Today, we're going to walk through exactly how it works, why it bypasses the limitations of scalar reward modeling, and how it translates structured evaluation directly into generative improvement. Let's start with a baseline. In standard preference learning, we typically rely on the Bradley-Terry model to parameterize human judgments. We train a reward model to output a scalar score, or we use pairwise comparisons to approximate a latent decision boundary. Both approaches entangle multiple quality dimensions into a single output. That works for coarse ranking, but it obscures preference structure. When you optimize against an opaque scalar, the model quickly learns to game the proxy rather than improve actual quality. Direct VLM judges fare slightly better, but they still suffer from persistent positional bias. Swap the order of two candidate images, and the judge's preference flips consistently, regardless of actual quality. Chain-of-thought prompting or positional labeling hasn't been able to reliably fix this. The bias is structural, baked into how implicit preferences are parameterized. ARR reframes this as a representation problem. Instead of learning weights to approximate a scalar reward, ARR externalizes the VLM's internalized preference knowledge into explicit, prompt-specific rubrics. And it does it training-free. The pipeline runs in 3 stages: generation, verification, and hierarchical structuring. Given a preference pair, the system prompts a frozen VLM to generate a natural language rubric that explains why one output is preferred. The prompt explicitly instructs the model to decompose the preference into independent, verifiable quality axes, avoiding holistic or comparative language that presupposes knowledge of both candidates. Once generated, each rubric is passed to a separate verification call. The verifier checks whether applying the rubric as an evaluation protocol correctly recovers the original preference label. If it fails, the rubric is refined iteratively, up to a fixed budget of attempts. In practice, about 87% of initial rubrics pass verification on the first try, and fewer than 4% are ultimately discarded. The verified rubrics are then consolidated by a structuring model that groups criteria by semantic granularity into a hierarchical protocol: coarse alignment, compositional structure, and fine-grained fidelity. This structured rubric becomes a system prompt for the judge and a conditioning signal for optimization. Crucially, this entire process requires 0 parameter updates to the judge. The rubric quality scales directly with the underlying VLM's alignment with human preference, without any additional supervision. Now, how do we turn these rubrics into a training signal? That's where rubric policy optimization comes in. Traditional RLHF collapses rubric-based evaluation into auxiliary filters or scalar composites. RPO does something different. It uses the RR-generated criteria to produce a binary preference decision, and feeds that directly into the policy gradient objective. For each prompt, the current policy samples 2 candidate outputs. The frozen ARR judge evaluates them against the structured rubric and outputs a binary preference. The winning trajectory receives a positive reward magnitude. The losing one receives a negative magnitude. Here's where it gets interesting for diffusion models. Instead of treating this as a sparse, terminal reward, RPO uniformly distributes the per-trajectory advantage across all denoising or generation time steps. You get a dense, per-step training signal that directly reflects rubric-guided preference. The optimization objective uses PPO-style clipping and KL regularization to bound the policy update and prevent excessive drift from the pretrained reference distribution. Because the reward comes from a frozen judge conditioned on explicit, verifiable criteria rather than a trainable scalar model, the gradient direction is grounded in interpretable dimensions of quality. This dramatically reduces the risk of reward hacking. The optimization target adapts naturally to the evolving distribution of the policy, conferring robustness against distributional shift. Let's look at the empirical results. The authors evaluate ARR as both a preference evaluator and a structured reward for generative policy optimization. On preference accuracy benchmarks like HPDV3, Reward Bench 2, and Edit Reward Bench, ARR conditioning consistently improves base VLM judges by 1.7 to 6.3 percentage points. More importantly, they quantify positional bias by measuring forward versus reverse accuracy on preference pairs. Base VLMs show massive gaps, with delta values between 30 and 34 points. Zero-shot ARR reduces this gap moderately, but when augmented with a small set of human preference exemplars, the gap collapses to under 10 points. This confirms that positional instability isn't a capacity limitation that resolves with scale. It's a structural deficiency in how preferences are implicitly encoded. Making evaluation criteria explicit anchors the judgment in criterion-level evidence, rather than holistic gestalt impressions that are highly susceptible to ordering heuristics. They also ablate rubric cardinality, testing how many criteria to generate per instance. Accuracy improves monotonically from 1 to 20 rubrics, demonstrating that finer-grained factorization captures genuinely complementary information rather than redundant coverage. They settle on 5 as a default for efficiency, but note that higher cardinality scales linearly with inference cost while consistently improving discriminative power. When deployed for generative training, RRPO pushes FLUX.1-dev and Qwen-Image-Edit significantly higher on text-to-image and image editing benchmarks. GenEval jumps from 0.66 to 0.80. DPG-Bench improves by nearly 2 points. TIIF and GenBench++ show consistent gains. The improvements require no reward model retraining, no architectural changes, and no large-scale annotation. The core mechanism is simply replacing opaque scalar regression with rubric-conditioned preference decisions. The takeaway here is structural. RRPO demonstrates that multimodal alignment isn't bottlenecked by a lack of preference knowledge. It's bottlenecked by the absence of a stable, factorized interface to apply it. By externalizing implicit preferences into explicit, independently verifiable constraints, ARR replaces unstable latent comparisons with grounded discrimination. RPO then translates that discrimination into robust, hack-resistant policy gradients. Evaluation and generation are unified through a shared preference representation, where better understanding of human preferences in evaluation directly strengthens generative alignment. If you're working on RLHF, reward modeling, or multimodal alignment, this is a clear example of how rethinking the reward interface can outperform scaling opaque proxies. The code is publicly available, and the appendix contains full prompt templates, hyperparameter schedules, and detailed ablation breakdowns. I'll leave the link in the description. Thanks for watching, and I'll see you in the next one.